Hello everyone, my name is Madhuri Gupta, working as an assistant professor in the Department of Computer Science, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Here is a quick recap of the last lecture on depth first search. Here is the definition. Depth first search is a graph traversal algorithm that explores as far as possible along each branch before backtracking. It starts from a selected node, that is source node, and traverses as deep as possible in the graph along each branch before backtracking. So, here are the advantages of DFS. First, simplicity. DFS is easy to understand and implement, making it a straightforward algorithm for graph traversal. Second, memory efficiency. DFS uses less memory compared to breadth first search, since it only needs to store the information related to the current branch being explored. Third, suitable for certain problems. DFS is particularly useful when searching for solutions in problems that involve backtracking, such as maze solving, finding path, and certain types of graph problems. Disadvantages of DFS. First, completeness. DFS may not find the shortest path in an unweighted graph because it explores a single branch as far as possible before trying other branches. As a result, it might not always find the optimal solution. Second, infinite branch problem. If the graph contains cycles and the algorithm is not implemented with appropriate punctuation, DFS may get stuck in an infinite loop leading to non-termination. Third, memory stack limitation. In some cases, the DFS algorithm can exceed the memory stack limit due to excessive recursion, especially on deep or infinite graphs. This can lead to a stack overflow error. Fourth, lack of guidance. DFS does not use any heuristic information, unlike some other search algorithm like A star search. This means it may explore paths that are less likely to lead to a solution, making it less efficient for certain problems. Overall, DFS is a powerful and simple graph traversal algorithm, but it has some limitations that need to be considered based on the specific problem and graph characteristics. In certain cases, alternatives algorithms like best first search or A star search might be more appropriate for finding optimal solutions or avoiding potential pitfalls. So, today we will discuss about heuristic search and one of the problem of heuristic search, that is hill climbing. Welcome to our exploration of heuristic search in the realm of artificial intelligence. In this session, we will delve into the fascinating concept of heuristic search, a critical technique that enables AI systems to efficiently navigate complex problem spaces and find optimal solutions. So, here is the definition of heuristic search. At its core, heuristic search is a method used to guide AI algorithms in making informed decisions about which path to explore in a search space. Unlike brute force methods that exhaustively explore all possibilities, heuristic search incorporates domain specific knowledge or heuristics to prioritize paths likely to lead to the best outcomes. The role of heuristics. Heuristic provide a way for AI to make intelligent guesses based on available information. These rules of thumb help AI system to evaluate the desirability of different states or actions within a problem. By combining heuristic with search algorithms such as best first search or A star search, we can significantly enhance the efficiency of finding solutions. A star search, a powerful heuristic method. A-star search is a widely used heuristic search algorithm that combines both breadth first search and greedy best first searches. It efficiently explores the search space by considering both the cost to reach a particular state and the estimated cost from that state to the goal state as provided by the heuristic functions. Heuristic search applications. Heuristic search techniques have a wide range of application across AI and computer science. First, pathfinding in games and robotics. Heuristic search helps game characters and robots find efficient paths in dynamic environments, avoiding obstacles and reaching their goals swiftly. Second, optimization problems. Heuristic search is used in optimization tasks such as finding the shortest route for delivering trucks or scheduling tasks to minimize time and resources. Third, scheduling and planning. AI planners employ heuristic search to create optimal schedule for tasks, ensuring efficient resource allocation and meeting deadlines. Fourth, natural language processing. Heuristic search assists in language generation, helping AI systems generate coherent and contextually relevant sentences. So, in conclusion, heuristic search is a crucial tool in the AI toolbox, allowing intelligent agent to navigate complex and vast problem space with efficiency. By incorporating domain specific knowledge through heuristic, AI system can make informed decisions and find optimal solutions even in the face of uncertainty. As we continue to advance in the field of AI, mastering heuristic search technique will undoubtedly play a pivotal role in creating smarter and more efficient AI agents. Let us understand the concept of heuristic search. Today we will discuss about hill climbing algorithms. Here is the visuals of mountain peaks. Heuristic search hill climbing algorithm. In this session, we will explore one of the most popular optimization algorithms, hill climbing, and how it utilizes heuristic information to find solution. So, let us dive right in. Before we delve into hill climbing, let us first understand what heuristic search is. Heuristic search is a problem solving technique that uses heuristic information or rules of thumb to guide the search towards finding a solution more efficiently. Now, let us introduce hill climbing. Hill climbing is a local search algorithm used for optimization problems. It starts with an initial solution and iteratively explores neighboring solutions, moving towards a better solution at each step until it reaches a local maximum or minimum depending on the problem type. The hill climbing algorithm consists of three main steps. First, initialization. We start with an initial solution which could be generated randomly or based on some prior knowledge. Second, evaluation. The algorithm evaluates the quality of the current solution using a heuristic function which provides an estimate of how close the solution is to the optimal one. Third, iteration. In this step, hill climbing examines neighboring solution, choosing the best one according to the heuristic evaluation. If the new solution is better, the algorithm moves to it and repeat the process, otherwise it terminates as it has reached a local maximum or minimum. Now that we know the basic steps of hill climbing, let us explore its advantages. First, simplicity. Hill climbing is easy to understand and implement, making it a popular choice for many optimization problems. Second, Memory efficiency. It doesn't require much memory to explore the current solution and its evaluation, making it suitable for problem with large search spaces. Third, quick convergence. Hill climbing can converge quickly to a local optimum for certain problems, making it efficient in those scenarios. Despite its strength, hill climbing has some limitations. Local optima. The algorithm can get stuck to local optima, meaning it might not find the global optimum solution if it exists. Second, lack of backtracking. Hill climbing doesn't backtrack, which can lead to missing potential better solution in the search space. Third, depend on initial solution. The quality of the final solution heavily depends on the initial solutions, and a poor initial choice may lead to a suboptimal result. Hill climbing finds application in various real world problems such as first, traveling salesman problem. Optimizing the shortest route for a salesman to visit multiple cities. Second, network routing. Finding the best path for data transmission in computer networks. Third, scheduling. Optimizing employees' shift or task assignments to minimize cost. Over time, several variations and improvements of hill climbing have been developed, such as first, simulated annealing introduces randomness to escape local optima and explore the search space more efficiently. Second, generic algorithms incorporate generic operators like mountain and crossover to perform more extensive search. Third, iterated local search combines hill climbing with random permutations to escape local optima. In conclusion, hill climbing is a fundamental heuristic search algorithm used to optimize various real world problems. Although it has its limitations, its simplicity and efficiency in certain scenarios make it an essential tool in the field of optimization. So, here is the hill climbing algorithm in artificial intelligence. Hill climbing algorithm is a local search algorithm which continuously moves in the direction of increasing elevation or value to find the peak of the mountain or best solution to the problem. It terminates when it reaches a peak value where no neighbor has a higher value. Next, hill climbing algorithm is a technique which is used for optimizing the mathematical problems. One of the widely discussed example of hill climbing algorithm is traveling salesman problem, in which we need to minimize the distance traveled by the salesperson. It is also called greedy local search, as it only looks to its good immediate neighbor state and not beyond that. A node of hill climbing algorithm has two components, which are state and value. Hill climbing is mostly used when a good heuristic is available. In this algorithm, we do not need to maintain and handle the search tree or graph, as it only keeps a single current state. Feature of hill climbing. Following are some main features of hill climbing algorithms. First, generate and test variant. Hill climbing is the variant of generate and test method. The generate and test method produce feedback which helps to decide which direction to move in the search space. Greedy approach. Hill climbing algorithm search moves in the direction which optimizes the cost. No backtracking. It does not backtrack the search space, as it does not remember the previous steps. State space diagram for hill climbing. The state space landscape is a graphical representation of the hill climbing algorithm, which is showing a graph between various states of algorithm and objective function or cost. On y axis, we have taken the function which can be an objective function or cost function and state space on the x axis. If the function on y axis is cost, then the goal of search is to find the global minimum and local minimum. If the function of y axis is objective function, then the goal of the search is to find the global maximum and local maximum. Here is the diagram for different regions in the state space landscape. Local maxima. Local maxima is a state which is better than its neighbor state, but there is also another state which is higher than it. Global maximum. Global maximum is the best possible state of state space landscape. It has the highest value of objective function. Current state. It is a state in a landscape diagram where an agent is currently present. Flat local maximum. It is a flat space in the landscape where all the neighbor state of current state have the same value. Shoulder. If a plateau region which has an uphill edge. Types of hill climbing algorithm. First, simple hill climbing. Next is steepest ascent hill climbing. Next is Scottish hill climbing. Now we will discuss about the first one, that is simple hill climbing. Simple hill climbing is the simple way to implement a hill climbing algorithm. It only evaluates the neighbor node state at a time and select the first one which optimizes current cost and set it as a current state. It only checks its one successor state, and if it finds better than the current state, then move else be in the same state. This algorithm has the following features: less time consuming, less optimal solution, and the solution is not guaranteed. Algorithm for simple hill climbing. Step 1. Evaluate the initial state. If it is a goal state, then return success and stop. Step 2. Loop until a solution is found or there is no new operator left to apply. Step 3. Select and apply an operator to the current step. Step 4. Check new state. A. If it is a goal state, then return success and quit. B. Else if it is better than the current state, then assign new state as a current state. C. Else if not better than the current state, then return to step 2. Step 5. Exit. Second algorithm is steepest ascent hill climbing. The steepest ascent algorithm is a variation of simple hill climbing algorithm. This diagram examines all the neighboring nodes of the current state and select one neighbor node which is closest to the goal state. The algorithm consumes more time as it searches for multiple neighbors. Algorithm for steepest ascent hill climbing. Step 1. Evaluate the initial state. If it is a goal state, then return success and stop, else make current state as initial state. Step 2. Loop until a solution is found or the current state does not change. A. Let success be a state such that any successor of the current state will be better than it. For each operator that applies to the current state, apply the new operator and generate a new state. Evaluate the new state. If it is a goal state, then return it and quit, else compare it to the successor. D. If it is better than the successor, then set new state as successor. E. If the successor is better than the current state, then set current state to successor. Step 5. Exit. Third algorithm is Scottistic hill climbing. Scottistic hill climbing does not examine for all its neighbor before moving. Rather, its search algorithm select one neighbor node at random and decide whether to choose it as a current state or examine another state. So, here is the problem in hill climbing algorithms. First, local maxima. A local maxima is a peak state in the landscape which is better than each of its neighboring state, but there is another state also present which is higher than that the local maxima. So, what is the solution? So, here is the solution. Backtracking technique can be solution to the local maximum in state space landscape. Create a list of promising path so that the algorithm can backtrack the search space and explore other paths as well. Here is the diagram for the local maximum. Second, plateau. A plateau is a flat area of the search space in which all neighbor state of the current state contains the same value. Because of this, algorithm does not find any best direction to move. A hill climbing search might be lost in the plateau area. So, what is the solution? The solution for the plateau is to make big steps or very little steps while searching to solve the problem. Randomly select a state which is far away from the current state, so it is possible that the algorithm could find non-plateau region. Here is the diagram for plateau. Third, ridges. A ridge is a spatial form of the local maximum. It has an area which is higher than its surrounding areas, but itself has a slope and cannot be reached in a single move. So, what is the solution? With the use of bidirectional search or by moving in different direction, we can improve this problem. Here is the diagram for ridge. Now, we will discuss some another method, that is simulated annealing, a hill climbing algorithm which never makes a move towards a lower value, guaranteed to be incomplete because it can get stuck on a local maximum. And if algorithm applies a random walk by moving a successor, then it may complete but not efficient. Simulated annealing is an algorithm which yields both efficiency and completeness. In mechanical term, annealing is a process of hardening a metal or glass to a high temperature, then cooling gradually. So, this allows the metal to reach a low energy cycline state. The same process is used in simulated annealing, in which the algorithm picks a random move instead of picking the best move. If the random move improves the state, then it follows the same path, otherwise the algorithm follows the path which has probably or less than 1, or it moves downhill and chooses another path. Here is the algorithm of hill climbing. First, initialize, start with an initial solution or state denoted as the current state. This initial state could be generated randomly or based on some prior knowledge. Evaluate, calculate the heuristic value or the objective function's value for the current state. The heuristic function provides an estimate of how close the current state is to the optimal solution. The objective is to minimize or maximize this value depending on the nature of the problem. Loop, generate neighbors, create neighboring state by making small changes to the current state. These changes are typically incremental modifications or permutations depending on the problem domain. Fourth, a select best neighbor. Evaluate each neighboring state using the heuristic function and select the neighbor with the best heuristic value. If multiple neighbors have the same value, you can choose randomly or use some tie breaking strategy. C, compare with current. Compare the best neighboring state's heuristic value with the current state's value. D, update. If the best neighboring heuristic value is better than the current state's value, set the current state to the best neighbor and go back to the step 2 with the new current state. Fifth, termination condition. The algorithm terminates when either the following condition is met: A, maximum number of iteration or a predefined stopping criteria is reached. There are no better neighbors than the current state. C, a time limit for the algorithm execution is exceeded. So, now we have the output. Once the algorithm terminates, the current state represents the best solution found by the hill climbing algorithm. Note that the hill climbing is a local search algorithm and does not guarantee finding the global optimum, especially in a complex and multi-model problem with multiple local optima. Various improvements and modifications such as stimulated annealing, generic algorithm and integrated local search are often used in enhanced hill climbing's performance and overcome the local optima and more complex optimization scenario. In our upcoming lecture, we will dive into our next heuristic search, especially focusing on the dynamic do best first search. This algorithm marks a significant shift from uninformed searches as they harness the power of heuristic to navigate through complex search space more efficiently. So, let us go started. Imagine you having a virtual guide that helps you take the most promising path towards your destination. Well, that is exactly what heuristic function do for our algorithms. This function provides an educated estimate of how close a state is to the goal, helping us prioritize our exploration. In this whirlwind tour, we have glimpsed the power of best first search. This algorithm transforms search process from mere exploration to purposeful navigation, opening doors to optimization solution. So, mark your calendar for our upcoming lecture. Get ready to embark on a journey where heuristic lead the way and algorithm like best first search redefine the art of finding solution. So, see you there. Thank you for joining us in this exploration of hill climbing algorithm and heuristic search. For more exciting content, until next time, happy optimizing.